Have you ever wondered how fast a satellite must travel to stay in orbit, or how long it takes to circle the Earth? In today's lesson, we're diving into satellite motion, connecting Newton's law of gravitation with Kepler's third law to calculate both the orbital velocity and the period of a satellite. We'll break it down step by step from the physics concepts to the math behind them, so you can see exactly how gravity keeps satellites in perfect balance between falling and moving forward. Let's get started and launch into some orbital physics. A satellite is orbiting a planet such as the Earth. The satellite is being constantly pulled toward the Earth. This is the force of gravity. This force of gravity will be exerting centripetal force on the satellite because the satellite is traveling perpendicular to the orbit. The satellite is both falling to the Earth and traveling horizontally, which causes it to form an arc. If the satellite's rate of fall and its horizontal velocity create a curve equal to that of the Earth, then we have a valid orbit for the satellite to travel in. The first set of formulas, we're going to deal with Newton's law of gravitation. The velocity will be measured in meters per second. The radius will be in meters. Sometimes you'll be given the radius of the planet, or you'll be given how far above the planet that the satellite is orbiting from. So if that's the case, you'll have to add the radius of the planet to how far above the surface the satellite is from the planet. The period will be measured in seconds. The mass of the objects will be measured in kilograms. So we'll start with force equals mass times acceleration. We also remember that force is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the two squared, where big G, which is gravitational constant, is equal to 6.67 times 10 to the negative 11, or you can say 2/3 times 10 to the negative 10. All right, my units will be newtons meter squared over kilogram squared, or I can also use meters cubed over kilograms second square. Okay, so let's see if we can derive a formula for velocity. So if we use F equals ma, okay, so I'm going to say this is the mass of the satellite here. I'm going to put an S there. And I'm going to put a C here for the acceleration because it's going to be centripetal acceleration. I'm going to substitute for the F this value here. So I'm going to say that G, I'm going to say mass of the planet times the mass of the satellite divided by the distance between their centers squared is equal to the mass of the satellite times the centripetal acceleration. Mass of the satellites will cancel on both sides. So I can say then that the centripetal acceleration is equal to gravitational constant times the mass of the planet divided the distance between the two centers squared. Okay, from circular motion, you should have learned that centripetal acceleration is equal to velocity squared divided by the radius. So let's substitute there. So velocity squared over radius is equal to g mass of the planet r squared. So I can say then that velocity squared, if I cross multiply, I will get g mass of the planet times r divided by r squared. So r cancels the square. So velocity squared is equal to g mass of the planet divided by r. So velocity is equal to the square root then of g mass of the planet divided by r. Okay, so this is a very useful formula where velocity is measured in meters per second. Mass of the planet will be in kilograms and the radius will be in meters. Okay, let's try a different formula. Okay, so this is from the center of the Earth. This is the center of the satellite. This is the radius. I know that the circumference of this is equal to 2 pi r. So I can say then that velocity is equal to the circumference divided by the time. So this time is going to be the period. So the period is the amount of time it takes for it to make one trip around. So we can say then that velocity is equal to 2 pi r over t. So this will be our two formulas that we'll use primarily for velocity when dealing with one thing going around one thing. Now we need to solve for the period. Okay, so we're going to start with velocity is equal to okay, so we're going to take the two formulas we just derived. So we can say that velocity is equal to 2 pi r over t, which is equal to the square root of g mass of the planet over radius. Let's square both sides. So I would have 4 pi squared r squared times r is equal to g mp t squared. Let's isolate the t squared. So t squared is equal to 4 pi squared times r cubed divided by g m's of p. Take the square root of both sides, so the period is going to equal the square root of 4 pi squared r cubed over gravitational constant times the mass of the planet. And I'm going to add one more thing. Let's take the 4 pi squared out. So that would be 2 pi times the square root of r to the third over g mp. Okay. So this is the period measured in seconds for the satellite to make one complete trip around the planet. So that gives us our two formulas for velocity and one for the period. Kepler's third law shows the relationship between the radius so this is radius 1, radius 2 versus the period. Okay, so let's see if we can show this relationship. Kepler found that the period was directly proportional to the radius of the orbits. So if this is satellite A, we can say that the period for satellite A is to the period of satellite B squared is equal to the radius for satellite A over the radius of satellite B, both raised to the third power. Okay, the period can be in seconds, it could be in days, years, so on and so forth. The radius here can be in meters, kilometers, astronomical units, whatever you desire. As long as both of these have the same units, and as long as these are the same units. Okay, for the first problem, I have Jupiter going around the sun, and I have Earth going around the sun. So I can say that the period of Jupiter is to the period of the Earth is the radius of Jupiter to the radius of the Earth. Okay, so that would be Jupiter's period of Jupiter squared over the period of the Earth squared radius of Jupiter to the third power over the radius of the Earth to the third power. Let's cross multiply and isolate our variables. All right, so we have tj squared re to the cubed equals te squared times rj to the cubed. All right, we're looking for the period of Jupiter. So let's divide both sides by the radius of the Earth to the third power. So we have the period of Jupiter squared is equal to the period of the Earth squared times the radius of Jupiter to the third power over radius of the Earth to the third power. Radius of Jupiter over radius of the Earth to the third power times the period of the Earth squared. The radius of Jupiter is 5.2 times that. So I'm going to say this is 5.2. The Earth is 1 unit. The Earth's period is 1.0 years. So I get the square root of, that'd be what, 141. So it'd be rounded off to 12 years. All right, the next problem, I have a planet and a satellite. So I have one thing going around one thing. I want to know what is the satellite's orbital speed and what is the period of the satellite. To calculate the velocity, we're going to use the formula. Velocity is equal to gravitational constant times the mass of the planet divided by the radius. So this is going to equal the square root of 6.67 times 10 to the negative 11th times 1.2 times 10 to the 24th divided by 2.0 times 10 to the 7th. This gives me the square root of 8.0 times 10 to the 13th divided by 2 times 10 to the 7th. So that gives me the square root of 4 times 10 to the 6th, which is equal to 2,000 meters per second, or you can say 2 kilometers per second. The period is going to be 2 pi r over the velocity. So this is going to be 2 pi times 2 times 10 to the 7th power divided by 2,000. So this gives me 2 pi times 10 to the 4th which equals 6.3 times 10 to the 4th seconds. Okay, the next problem, we have a satellite orbiting the Earth in a geosynchronous circular orbit above the equator. What's the radius of the satellite's orbit? We'll use 6 times 10 to the 24 kilograms for the mass of the Earth. So I have one thing going around one thing. So I can say then that the period is equal to 2 pi times the square root of r cubed over gravitational constant times the mass of the planet. All right, let's square both sides. So t squared is equal to 4 pi squared r cubed over g mp. Let's get r cubed by itself. So r cubed is equal to t squared multiplying across g, mass of the planet, and we'll divide coming across the other way. So it'll be 4 pi squared. So the radius is equal to the cube root of t squared g mp over 4 pi squared. So the radius is going to be the cubed root. The period. The period is the time it takes for 1 year. Okay, so that'll be 86,400 seconds. Times g. Times the mass of the planet. Divided by 4 pi squared. So the radius is equal to the cube root 746,496 times 10 to the 18th power divided by pi squared. So the radius is equal to 4.23 times 10 to the 7th meters. Okay, the next problem, I have an asteroid orbiting the sun, and I want to measure it in Earth years. I'm comparing two things, an asteroid and the Earth, both going around the sun. So I'm going to use Kepler's third law. So the period of the asteroid over a period of the Earth is equal to the radius of the asteroid over radius of the Earth. Okay, I'm looking for the period of the asteroid. I'm going to cross multiply. Okay, I'm looking for the period of the asteroids. I'm going to divide both sides by the radius of the Earth. Okay, so the period of the asteroid squared is going to equal the period of the Earth. Well, the period of the Earth is 1 year. Times the radius of the asteroid to the third power. So it's going to be 3 times 10 to the 11th power raised to the third power divided by the radius of the Earth. The Earth is 1.5 times 10 to the 11th. That will be to the third power also. So TA squared is 3, that'll be 2 to the third power. So TA squared is equal to 8. So TA then will be equal to the square root of 8, which is approximately 2.8 years. Every 74 years, Comet Halley is visible from Earth. Find the average distance of the comet from the Sun in AUs, or astronomical units. Have two things going around one thing. So the period of Halley over the period of Earth the radius of Halley over the radius from the Earth. Since I'm comparing it to Earth, I can say 74 years over 1 year squared is equal to radius of Halley's to the third power, and Earth is 1 AU. So this simplifies then into radius of Halley to the third power is equal to 74 to the second power. The radius of Halley's will be the cube root of 74 squared. So the radius of Halley is equal to approximately 17.4 astronomical units. And that wraps up our exploration of satellite motion, where Newton's law of gravitation meets Kepler's third law to explain how satellites stay in orbit. We've seen how gravitational force provides a centripetal pull that keeps a satellite moving in a circular path, and how those relationships let us calculate both orbital velocity and the period. If this video helped you understand the physics behind orbital motion, give it a thumbs up and share it with your classmates. Don't forget to subscribe and hit the notification bell so you don't miss an upcoming lesson. Thank you for watching.